Good evening. Today we start a new chapter, Waves, which is the last chapter for our syllabus in class 11 this year. Now, as I speak to you, there is sound energy that is being transmitted from me to the listener. So, this energy that I produce, the sound energy, sets into vibration the particle that is closest, the air molecule that is very close to my mouth, is receiving that energy and it starts oscillating about its mean position or vibrating about its mean position. It transfers that energy to the next neighboring particle, setting it into oscillation. That particle then transfers the energy to the next particle, putting it also into oscillation, and thereby the energy is transferred from my mouth to the ear of the listener. But the particles of the medium are not actually transferred from one point to another point in the medium. So here you see that the particles of the medium are simply set into oscillation or vibration because they receive energy from the source, but this energy is being transmitted from one point to another point in the medium. So such a transfer of energy and therefore momentum from one point to another point in a medium, whereas there is no transfer of the particles of the medium from one point to another point, this is what you call as wave motion. So basically, in wave motion, the energy is transferred, but the particles of the medium simply oscillate about their own position. They do not move from the source to the listener or from the source to wherever the energy has reached. Now, you can have two types of waves. One is called the transverse wave and the other is called the longitudinal wave. So if you have the source here, and let's say we have a point A and a point B in a medium, and the wave or the energy is transmitted from one particle to the other particle, but the particles, as I said, do not move, but the energy is being transmitted or the wave is moving or propagating from A to B. And if the particles of the medium vibrate about a mean position, which is perpendicular to the direction of propagation of the wave, such a wave is what you call as a transverse wave. So here what I've drawn is a transverse wave. Each of these particles of the medium are oscillating in a direction that is perpendicular to the direction of propagation of the wave. Such a wave is what you call a transverse wave, and the transverse wave propagates in the form of what you call as crest and troughs. So the crest is the maximum displacement along the positive direction and from the mean position, and the trough is the maximum displacement in the negative direction from the mean position. So a transverse wave propagates in the form of crest and trough. Now if you talk about a longitudinal wave, the energy, imagine the energy, the sound energy is traveling from A to B, but the particles of the medium oscillate in a direction parallel to the direction of propagation of the wave. So these particles are also set into oscillation, but the direction of oscillation is parallel to the direction of propagation of the wave. Such a wave is what you call as a longitudinal wave. Now what happens in a longitudinal wave is, because they are oscillating in a direction parallel to the direction of propagation of the wave, you will see there are regions where the particles come close together. There are also regions where the particles are further away. Then again you are having particles which are closer, and then again we have particles which are further away, and so on. These regions are what you call as a compression, and these regions where the particles are further away from each other is what you call as a rarefaction. And so a longitudinal wave travels in the form of compressions and rarefactions. So we have just discussed the two types of waves. One, the transverse wave, in which the particles of the medium oscillate in a direction perpendicular to the direction of propagation of the wave, and they travel in the form of crests and troughs. And a good example of a transverse wave is any electromagnetic wave, like the light wave is a transverse wave. So is the wave set up on a stretched string, like in the example of a guitar string. When you pluck the string, the waves travel as a transverse wave. And we then discussed about longitudinal waves, where the particles of the medium oscillate in a direction parallel to the direction of propagation of the wave, and they travel in the form of compressions and rarefactions. And a good example of a longitudinal wave is a sound wave. Now, so here we next discuss certain physical characteristics of the wave. The first thing we need to look at is the amplitude. The amplitude of a wave is the max. All of these particles are vibrating about their mean position. The maximum displacement of a particle of the medium from their mean position is what you call as amplitude. And so this is also the amplitude. The maximum displacement of a particle from its mean position is called the amplitude, measured in the SI unit meter. We also need to look at wavelength. Wavelength is the distance between two crests. We have a crest here and here. Two consecutive crests, or the distance between two troughs, is what you would call as one wavelength, also measured in SI unit meters. Then we have to look at frequency. Frequency is the number of waves, or the number of cycles, or the number of waves that pass through a given point in the medium in 1 second, and that is measured in number of cycles per second or in hertz. And we know this frequency is, wavelength is denoted as lambda, frequency as nu. So these are the physical characteristics of a wave. Also, both transverse wave and longitudinal waves are called progressive waves or traveling waves, because even though the particles of the medium do not move from one point to another point, energy is transferred, momentum is transferred from one point to another point, and therefore we say the wave is a traveling wave or a progressive wave. Now, as we enter into this traveling waves, or what we call as progressive waves, we have a displacement relation which can represent a traveling wave or a progressive wave, given as y equal to a sine kx minus omega t plus phi, where so this represents a traveling wave or a progressive wave. Here y stands for the instantaneous displacement of a particle of the medium. That is, for example, let's say we look at this particle here, which is at a position x from the origin. At any instant of time, its displacement from the mean position along the y-axis, this is what we call as y. So y is the instantaneous displacement of a particle which is at a distance x from the origin at a given instant of time t. So it is actually written as y of xt, that is instantaneous displacement at a given instant, a particle which is at a distance x. This could be any other. So you will see y for this particle at this position x is this. Now if you're looking at another particle, let's say the particle which is here at the origin, then x is 0, and at that particular instant the displacement of the particle is 0 from the mean position. So you could be also looking at a particle, let's say at this position, which is at a distance x from the origin. The instantaneous displacement of the particle, the displacement along the y-axis of that particle at that instant is what you denote as y. Now A, as I mentioned to you, is the amplitude, which is the maximum displacement a particle can have from the mean position, is what you call as the amplitude. We now have K, which is called the wave number, which is the number of waves present in 1 meter, in unit meter of the medium. So that means if you have, let's say we have the wave traveling like this, and let's say this is 1 meter of the medium. So if you have a small wavelength, we can have a larger number of waves in 1 meter. Instead, if the wavelength is very large, then the number of waves present in 1 meter will be smaller. So here, wave number is the number of waves present in unit length of the medium, which is, you see, inversely proportional to lambda. This is 1 lambda. So you will see that this K, that is the wave number, is inversely proportional to lambda, or K is equal to a constant 2 pi by lambda, 2 pi in radian and lambda in meter. So the SI unit of K is radian per meter. Then we see that you already know about omega being the angular frequency related to the linear frequency as 2 pi nu, where the angular frequency is given as radian per second, nu being the number of cycles or waves crossing a crossing a point in the medium in 1 second. Then we go on to look at phi, which is called the initial phase or the phase constant. That is, now if you look at two waves that I've drawn here, one with a bold line and the other with a dotted line, you will see that the amplitude of both the waves are the same. The frequency is also the same. The number of waves that I've drawn in 1 second, in one time period, is also the same. But you will see that they have shifted a little. That is, this is T by 4. If I divide, this is one time period. This is 1/4. This is half the time period, 3/4 the time period, and one full time period. So if you look at T by 4, the angle difference is pi by 2. This is pi, 3 pi by 2, and completed 2 pi. So you will see here that this wave and this wave are shifted by an angle pi by 2. So the phase difference being pi by 2. So here if I take phi equal to 0, you see if we are looking at a particle at the origin, we know x is 0, at the time equal to 0, and if phi equal to 0, then we know y is going to be a sine 0, which is simply 0. That means a particle at the origin at time t is expected to have 0 displacement from the mean. It is supposed to be at the mean position at time t equal to 0, a particle which is at the origin, in which case the phase constant is 0. But instead, at time t equal to 0, at x equal to 0, if the particle is already at the maximum displacement, that is y equal to a, then the phase constant would be pi by 2, because you take x equal to 0. We are talking about a particle at the origin at time t equal to 0, but phase being equal to the initial phase is pi by 2, would mean that this is 0, but this is pi by 2. So a sine pi by 2, sine pi by 2 being 1, y would be equal to sine pi by 2 here, and y equal to a. So this wave which I have drawn with a bold line has a phase constant, initial phase phi equal to 0, but the dotted one has a phase constant, the initial phase being equal to pi by 2. So this is what we mean by initial phase or phase constant. Now we need to look at this kx minus omega t. So if you are now looking at a wave with a phase constant phi equal to 0, we may simplify the equation to y equal to a sine kx minus omega t, where kx minus omega t is called the phase of the wave. So the phase of a wave is a constant, so which means kx minus omega t equal to a constant. Now if I differentiate this with respect to time, we have k into dx by dt minus omega equal to 0, or dx by dt equal to omega by k, or dx by dt is what we have as the velocity of the wave, which is positive. So you see, if you see the phase represented as kx minus omega t, we know that the velocity is positive omega by k, which means the velocity is towards the wave is traveling along the positive x-axis. On the other hand, if you see that the phase of the wave is represented as kx plus omega t, then we have kx plus omega t a constant, or k into dx by dt plus omega equal to 0, or dx by dt being equal to minus omega by k, showing you that the velocity of the wave is in the negative x-axis. So if you see the phase represented as kx plus omega t, you need to know that the velocity of the wave, which is omega by k, will be towards the negative, in the negative x-axis, along the negative x-axis. So v omega by k. Now I may multiply this by 2 pi, and divide by 2 pi, you know that omega by 2 pi is nu and 2 pi by k is lambda. I just told you that k is 2 pi by lambda. So I replace 2 pi by k as lambda. So we have our equation V equal to nu lambda. So this is how you would represent a traveling wave. We will continue our discussion in the next session. Thank you.